Thank you all for joining in. My name is Filip Lemic, and the title of my talk is Experimental Validation of IEEE 802.11ah Propagation Models in Heterogeneous Smart City Environments. So I will start by saying a few words about IEEE 802.11ah technology. It is a relatively novel sub-gigahertz license-free Wi-Fi technology. It is particularly interesting in the context of smart cities. This is primarily due to its long range compared to other Wi-Fi technologies, low energy consumption, and ubiquitousness because it is a Wi-Fi technology. It is intuitive that many of IEEE 802.11ah based systems will use propagation modeling. This is based on the observation that many other wireless communication technologies or systems make use of propagation modeling. Uh, so the aim of this work is to establish the applicability of the existing propagation models for the IEEE 802.11ah technology. This is a bit problematic because at the moment when we were doing this research, the hardware for 802.11ah did not exist. This was roughly 9 months ago. We're not sure if it exists yet. So we managed to establish the suitability of existing propagation models, and indeed it will show that we believe they're suitable. However, we will also show that there will be a need for environment-tailored design of IEEE 802.11ah systems that make use of propagation modeling. So a bit more about IEEE 802.11ah. It's a technology that is serving kind of like a bridge between Wi-Fi on the one hand side and LPWAN, low power wide area networks technologies, on the other. And this is depicted on the left-hand side in the graph. So you can see that in terms of range, it's in between the two different types of technologies. And this is why it is particularly interesting. In the table, you can see the main features of different low power wide area network technologies. Here again, you can see that 802.11ah provides higher data rates in comparison to LPWAN, other different LPWAN technologies, and higher and lower range. So that being said, these are the off-the-shelf propagation models that we have considered. The first one is the COS231 the second one is Wolfish Ikegami, third one is ITUR below rooftop, and then three propagation models taken from 802.11ah standard. As you can see on the slide, these models somehow model the path loss based on different input parameters, mostly frequency, you can see it here, distance between the devices, and then some additional parameters for some model. For example, the ITUR distinguishes between line of sight and non-line of sight conditions based on the distance between the devices, while, for example, COS231 use additional parameters such as the height of the base station and the height of the mobile device. So I mentioned at the beginning that there is no IEEE 802.11ah hardware currently available. So the question was how to experimentally evaluate the suitability of these off-the-shelf propagation models without the proper 802.11ah hardware. In order to do so, one should observe on the left-hand side the modulation and coding scheme table taken from the E.AH standard. And what should see that modulation coding schemes 1 and 3 on the left-hand side in the table are equal, at least in terms of modulation, encoding rate, and frequency repetitions to the modulation encoding schemes of 802.11.15.4g standard. One should also note that the data rates, the supported data rates by the two standards are not the same, they're different, but the open modes that we use for performing the measurement campaign support bandwidths, and data rates that are compliant, minimum data range compliant with 802.11ah. So in our evaluation, we managed to evaluate something that we believe resembles 802.11ah standards. In particular, its modulation and coding indexes 1 and 3. So this is the measurement setup that we have used for our measurement campaign. On the left-hand side, it's the server side, which is positioned in a fixed location. And then on the right-hand side is the receiver, so client side, kind of the receiver side, which has been moved to different locations in the environments of interest at different distances from the client side, from the transmitting side. The client side consists of a laptop that is connected to an electricity grid, and to a laptop there is we connected one open mode, which served as a mode as transmitter. And then we're transmitting 802.11ah packets in a sub-gigahertz frequencies, as shown here. On the client side, we use the Raspberry Pi, which was powered through a power bank. To a Raspberry Pi, we attached the GPS receiver for logging the locations where the measurements were taken. And the GPS receiver was used only for the outdoor environments where GPS performs solidly, while for the indoor environment, we were actually measuring the distances between devices. I will come to that later. And to the receiver, we've connected to the Raspberry Pi, we've connected the open mode, the receiving open mode. We have considered in our measurement campaigns three different types of environments. We call the first one the suburban environment, where the measurements were collected in the suburban area of the city of Antwerp in Belgium. And this has been done with so the connectivity is mostly the line of sight connectivity between the devices. This is depicted in the footprint of the measurement area with this pin indicating the location of the transmitter, while the blue points indicate the locations of the receiving end. We also considered an urban environment, which is a residential neighborhood in the city of Antwerp. You can see here with mostly non-line of sight connectivity. And we have also considered an indoor environment, which is a university building of the University of Antwerp, where again, we've observed mostly non-line of sight connectivity. The floor plans or the footprints of these environments and measurements locations are depicted in the slide. So this is the first set of the results. In the graphs, in the first row, you can see the results for three different types of environment for the modulation and coding scheme 1. While in the bottom row, you can see that the same thing for the modulation and coding scheme 3. On the x-axis, we have a distance between the devices in each graph. On the y-axis, we have the path loss, the measured, and the modeled path loss. So the blue dots in the figures depict the measured path losses at different distances between the devices, while the lines of the different colors depict the modeled path losses using different off-the-shelf propagation models. This is the summary of the mean absolute errors, so the difference between the measured values and the modeled values of all environments, for all environments and for different modulation and coding schemes, for the suburban environment, for the urban environment, and for the indoor environment. And so what we can see from these mean absolute errors is, first, for some propagation models, these mean absolute errors are relatively small. So these are less than around 2 to 3 to 4 dB, which we believe shows that the existing propagation models are indeed suitable for 802.11ah. In terms of their performance, we can see that for the scenario 1, which is suburban environment, the AH-PICO is the best performing model. For the urban environment, the best performing model is COS231-HATA, while for the indoor environment, the best performing is the Wolfish Ikegami model. The observation that different models perform best in different types of environments, and then in some models also, for example, walking fish ikegami performs very good for an indoor environment, while it provides almost the worst performance. Almost the worst performance for scenario one. So this indicates that there will most probably be a need for environment-specific propagation modeling in 802.11ah. The second set of results is depicting the observed packet losses. So although the effective range is high for scenario one, which is depicted here, it's around 1 kilometer. For the urban is around 600 meters, and for the indoor is around 50 meters. The packet loss, which is depicted here, increases rapidly even at the half of the achievable range. Which is, and this is kind of, these results are summarized here. You can see the packet losses as a function of distances. So this first row depicts packet loss of 0%, which can be achieved for 200 meters for the scenario one, 120 meters scenario two, etc. So the conclusion here is that even if nominally the communication can be established, packet losses can be high. And this is a behavior that is more pronounced for higher MCSs. So we can see here that for MCS1, we can achieve 90% packet reception at 240 meters, while for MCS3, this range drops to 32 meters, which is not a lot. So the conclusion here is that it seems imperative to use low MCS values for highly reliable communication, especially in indoor and urban types of environments. It also seems imperative to be conservative in propagation modeling, or to consider only connectivity at half of the range if the goal is highly reliable communication, because roughly speaking, as a rule of thumb, as we go further than half of the range, the packet reception rate seems to be dropping rapidly. And this is it. I'm just going to make a few conclusions. The first one is that, as I mentioned before, existing off-the-shelf models are indeed suitable for 802.11ah. Accuracy of the modeling is environment dependent, which suggests that the deployment should be environment tailored. I also want to emphasize that the presented research was performed as a part of a student internship, so mostly Tobia de Koninck did the work, and this research, this initial research, was extended to 802.11ah network discovery and vertical handover. Uh, uh, and this has been published as a part of the Tobias master thesis at the University of Antwerp. So I will take this opportunity to congratulate Tobia on his work. And if you have any questions, please do ask me.